So this is a bit of review. We're just going over the wave functions and properties of the particle in a box wave functions that we've covered over the past few days. Whoops.
Bear with me a second. Okay. There it is.
All right, where everybody's here. Very good. Yes, that's the kinetic energy. The kinetic energy is the curvature of the wave function. And so the lobes is where the curvature is the highest. That's where the kinetic energy is. When you square that wave function, all of the lobes become positive when you square the wave function. And the square of the wave function is called what? Vocabulary word. The square of the wave function. There's one word really associated with it. It should be two, but the square of the wave function is associated with what? Okay, go back to your Quizlets. Probability distribution. So what is distribution? It's how the particle is distributed between the boundaries. And it's a probability. So if it's 4 bumps, each bump is a fourth. A fourth of that particle, you have a 1/4 probability of finding the particle in the first bump, second bump, third bump, or fourth bump. Okay. Okay, question 2. Derivative of cosine x is, quickly. Very good. Why is the sine of 2n pi L over L 0? This is a useful skill in your lab. Nice. Those multiples of, integer multiples of pi is 0. What happens to the energy level spacing as L increases? Very good, because that L is in the denominator, so if it gets big, the energy drops of all the quantum states, so they get closer and closer together. We're going to talk about this particle in a box problem really all year if you go into thermodynamics. And it's supposed to represent translational motion. So even a particle in this room would be a particle in a box. And boundaries this big, the L is huge. And so the energy level spacings are so close together we can't detect the differences. So we could not detect the translational quantization of a nitrogen molecule in this room because L is too big. We couldn't see the energy differences. Last one. What happens to the energy level spacing as M increases? So you're looking at that equation. Where is M? My goal for you is to be able to look at an equation and read it like a paragraph. And you find all the pieces and you're able to pull out facts from that equation. So once again, M is in the denominator. So a massive particle like myself, you would not be able to detect my quantized states in this room. All right, congratulations. So let's talk now about